I think all the chat we're all set. So I guess welcome everyone to our penultimate AME seminar for the spring semester. There'll be one more in 2 weeks. This week we're very happy to have Shiwei Zhang here from the Flatiron Institute, and also William and Mary, who's going to be talking about learning, understanding, and predicting quantum phases for two-dimensional materials. So, Shiwei, take it away.
Thank you, Anil. Thanks everybody for coming. It's such a pleasure to be here. We couldn't quite figure out the cursor, so hopefully there's enough animation for this to still work. So I'm going to talk about 2D materials. As I think many of you are aware, there's been amazing exponential progress in two-dimensional materials. So now they form a rather diverse set of tunable platforms for exploring, understanding, and engineering quantum phases of matter that just has a lot of flexibility and new possibilities. So what I wanted to convey, the basic message is the neural network is providing really a promising tool to learn and discover new physics in this realm, but when used well, when used with caution and properly. So quantum materials, of course, are engine for quantum revolution. This next line came from, I think, a Microsoft propaganda for their co-piloted quantum computing thing. I wasn't sure about the rest of the message, but I totally agree with this statement that these materials affect 96% of manufactured goods. I don't quite know how that was estimated, but it sounds correct, and certainly 100% of humanity. The goal of having a materials genome project clearly rests on predictive ab initio computations. Without that, especially at the bottom level, ab initio level, then everything else will not be as robust. The usual approach where we use, for example, density functional theory and then force fields and so on, doesn't work as well in strongly correlated materials. I think this also you're familiar with, for example, many transition metal systems. A really prototypical example that's mentioned over and over is the family of cuprate materials, high TC superconductors. These figures, which you can't see, but depict a sequence of them, the basic structure, geometry, and then the bottom is this picture that you've undoubtedly seen of the floating material under a magnet. So the Hubbard model has played a central role in our effort to try to understand these materials. And I think you're also familiar with this, but it's the simplest two-dimensional model you could think of that combines both band structure and interaction. So electrons of two spins up and down here live on a lattice, and they can hop to a near neighbor. And when two of them in the middle are on the same site, they pick up a repulsion U. And this simple local interaction and this local action of hopping, the interaction with kinetic energy.
Shiwei,
Yeah.
can you hear us? I think your slides are not being passed.
Oh, interesting. Sorry. I see that in the screen. So
That's what I was just making sure it wasn't just me.
let me try to share again. Let's see.
Shiwei, can you try to advance?
Yeah. It's still not moving though.
It's
I
not
see
moving.
No, it is not.
If you showed it in the view that you just had, like we can see it well enough.
Mm-hmm.
Like if you just showed the slides as you make them, basically.
Like this.
Yeah, this is fine.
Yeah, this would be.
Yeah, we can see.
But this would be horrible because all the animations would be gone. I don't know. I guess our peak proficiency with virtual talk, certainly for me, was several years back. Uh, so
w- which slides have animations?
well, at least they are just sort of, I advanced them since I don't have the pointer doing very well. It's kind of
Um,
are you seeing any movement?
It takes time to actually show the first slide, which I think might be it.
Keynote.
Oh.
Oh, now it has changed. It's a new slide.
Oh, let's see if it gets stuck there.
Can you try to move like
Yeah, I'm moving.
advance?
It's not showing.
It's not showing.
Yeah, it does not.
How about we just go back to the
So let me do something. I'm on my in my office on the screen. Let me just go to my laptop and do the same. Let me kill the double screen, the panel. See if well, sorry about that. Bye. Let's see. What do you see now?
we see the first page.
Title
Can you try to
slide.
advance?
Okay. Still not showing, I think.
What if you export to PowerPoint? Somehow Zoom and Keynote do not seem to be friends. I think I've seen issues with Keynote before. Can you export to PowerPoint and play the PowerPoint? Uh,
I'm doing a PDF. We'll see how that.
I just looked up and it says there is set Keynote to play in a window. Maybe there is an option to play in window, whatever that means. If you go to on your Keynote, if you go to play on the top menu,
Yeah.
there is apparently in window option that prevent Keynotes from taking over your screen and allow Zoom controls to remain visible or something like that.
Play. Mine doesn't show that.
I see.
It's a play
Then
button.
let's do PDF. PDF or
Let me
PowerPoint
try that. Let me
export.
try
Yeah.
the PDF. Okay.
Yeah, somehow Keynote and Zoom are not friends. I've seen this issue before.
Shiwei, give it one more try because when you go to sharing, you have an option of sharing the entire screen, and that's probably what you are sharing. But you can go and share application window.
Yeah, I think I had tried both, but let me try again. Share all application windows.
Or maybe you can hop on a bus.
Yeah, it would, at this rate, that would be faster, wouldn't it?
Well, we see
I see the
cursor
cursor
now.
now.
That's great.
Okay. Do you
Oh,
see?
it worked.
Yeah,
You
nice.
advanced.
All
This is
right.
working. Whatever you did is working.
No, whatever you told me to do is working. The AI
Ah.
Institute is definitely doing things.
Okay, good. Let's start.
I'll need to
Start.
back up.
Start.
Okay. Sorry
Let's
about
get
that.
going. Yeah, keep going now.
Right.
Now you can. You
So you
have
see a full
mouse.
screen. Okay. So I was telling you about how reminding you of the 2D the progress in 2D materials, and then saying that what I hope to convey with the reduced time is that neural networks are providing a promising tool to learn and discover new physics, but when used properly and well. So in terms of the quantum revolution, quantum materials affect manufactured goods, and of course are very, very relevant to us. This is what I was mumbling about Microsoft Copilot marketing material. But predictive ab initio computations are important, are foundation for any materials genome initiative. And the usual approach, as we know, with density functional theory and then force field and so on, doesn't work well in so-called strongly correlated materials. And this is a somewhat circular definition, right? We call them strongly correlated when the usual mean field type of picture doesn't work well. But for example, the prototypical system of cuprates shown here, the family of materials. So the Hubbard model has played a central role in our effort to try to understand these materials. And this is a little cartoon of the Hubbard model. I think you're all familiar with it, but simplest picture of that combines band structure and interaction. The electrons of two kinds of spins, blue and red, hop to a near neighbor. And in the middle, when two of them are on the same site, they pick up a repulsion. And this entangles the whole system, and it's deceptively complicated. It's sort of the icing model of quantum many-body physics, but with the key distinction that the icing model we have now been able to solve, at least computationally in 3D, but this model we don't quite know how to solve. So in the context of high TC, one of the questions is, does it capture the basic physics of cuprates? So what we learned through the years is that competing and intertwined orders, they tend to be separated by very tiny energy scales. And this is not just to the Hubbard model, but certainly is in the Hubbard model. For example, in the Hubbard model, we've learned that if you care about superconductivity, which we do, the pairing correlation function that you need to detect is on the order of 10 to the minus 4, if it's there. So it's very easy to get wrong answers. There's an infinite number of ways you could get the wrong answer. There's a lot of danger of doing misleading calculations, or whether it's AI assisted or not. This is just to illustrate that. What I'm showing is at half fitting, where one could do exact quantum Monte Carlo calculations as a function of system size. So this is plotted inverse system size. So as you go to the left, you're trying to get to the thermodynamic limit. If you do a usual thing with periodic boundary conditions, I've listed. So for example, 4 by 4, you could diagonalize. And then 6 by 6, you cannot anymore. 8 by 8, these are all exact numbers, 10 by 10. 10 by 10 would be a very impressive calculation already, and in this case, that happens to be exact. And if you did the extrapolation with this, you would do this, and you would hit on the left axis an energy, which is slightly below this black dot I showed you. The black dot does a trick that does twist average boundary conditions, meaning it's like in band structure where you do a Brillouin zone integration very well. And that's the exact answer. So you make a tiny, by all measure, you don't care. But you've noticed that the red curve kind of curves up. We've pushed it to bigger systems. You can see this curved up and goes there. But that little bit of difference is the difference between seeing a state like this, where the blue and red electrons are antiferromagnetically aligned with a modulation. So this is a stripe or spin density wave state. This is now we've understood. It's the ground state of the usual Hubbard model. It's between this versus getting something else, like a phase separation, and that's the energy difference. So then imagine adding the complexity from material specificity, that lattice structure that we showed for the cuprates. So it's very, very hard. So lessons from 4 decades trying to understand cuprates, these intertwined states, there's always a very delicate balance of small energy differences. So you need high accuracy quantum many-body methods. The fundamental challenge is that there's no general algorithm that would just work, right? Versus for most, except chaotic systems, most glassy systems, most classical systems, you could carry out, or statistical physics at finite temperature, molecular dynamics, Monte Carlo, and you can make impressive progress on that. And here, you don't have sort of that method to do that. And the Simon's collaboration on the many-electron problem, which now is more than a decade, started more than a decade ago, and then it ended, and its continuation is kind of CCQ now, where I am. So one of the things we learned through this decade of effort is that you develop methods, you benchmark them very, very carefully, and you collaborate. You hit these hard systems with many methods together to try to extract the insight. So of course, a bit of bragging here in terms of understanding superconductivity. This is our latest. And you can see that compared to the experimental dome, what we found is that with the right T prime that models the cuprate band structure, it seems to have a lot of the basic features. So I mentioned this as a little thing to sort of as a lesson as we try to explore new methods to understand the context. So now to Moray materials. As I said before, they offer many exciting possibilities. So here's bilayer graphene. What you do is in this left figure, you twist and you form these Moray patterns. And in this pattern, this is a nice picture produced by a review paper. I'm sorry, I had it somewhere, the reference. So this is the density of states plotted in this plane. You can see corresponding to these puddles, there's more phase space for electrons to live. And correspondingly, the band flatten. And so the kinetic energy for the electrons is lowered. So the Moray system, it creates a new length scale. That's this lambda indicated on the left. That's much longer. And then there's a flat band, which lowers kinetic energy. So all of this creates very strongly interacting systems. In other words, relative to the kinetic energy or the band, the interaction energy is enhanced. And there's a bunch of interesting phase diagrams. And you can see that, for example, the leftmost one, it reminds you of the high TC. And of course, Cornell, there's a very, very active experimental effort there. And many different aspects of theoretical efforts as well among people in the audience. So this is different layers. And you can see that, as you add layers, interesting things emerge. So these exotic phases. And this is the other main platform, the TMDs. Similar things that you can have these metallic gates to tune charge carrier and then control the displacement field. And then exotic phases appear again. So this is the anomalous Hall effect. And then there's when you tune the polarization here on the horizontal axis and the carrier, you produce charge orders, Hall effects, and superconductivity as well. So this is what I promised you, but in terms of the materials, the 2D materials, the enhanced role of Coulomb interaction now creates a magnified view of the interplay with kinetic energy, between kinetic energy and Moray and topology. So chances for understanding new physics and this resemblance between the phase diagram, for example, another window that's more tunable, for example, to understand high TC materials as well. So what I'm going to focus on in this talk is a simplified model for these systems that looks like this, that you have a two-dimensional system of electrons, and these are supposed to show their spins. They don't have to be fixed later. They're spinners with topology. But you have a kinetic energy of the electrons and this Moiré potential, which creates these puddles to mimic the, for example, in the top figure. And then the Coulomb interaction, which can be screened. We can change the different form, but basically it's quite long-ranged. So this is the system we're going to try to study, and then you can add additional things as we will, disorders and so on. And we want to look at, and now there's interesting interplay between, electron density and interaction and so on. So this is the Hamiltonian we target, and we're interested in ground state phase diagrams. We're interested in additional things too, but I'm going to only tell you about ground states. So a few different things, time permitting. Going to tell you about new physics in a very old system, the plain 2-dig, the two-dimensional electron gas with no Moiré potential. And then disorder, where we have done a recent collaboration with experiments with STM. And then a new state called paired Wigner crystal in a honeycomb Moiré. And then finally, if there's time, a little bit about anomalous Hall crystals. So what I want to give you a sense is kind of a frontline view of, in this context, quantum many-body computations, what AI cannot do right now. So the two-dimensional electron gas, the same Hamiltonian now, this is imagine particles in a box. Kinetic energy written in an atomic unit, Coulomb interaction, and a uniform background to offset so that the whole system is charge balanced. So this system is specified by a single parameter, which is the average separation of electrons called RS. So imagine that, if you take the whole volume or area divided by the total number of electrons, that gives the area for each electron, and the radius corresponding to that is RS. So that's the single parameter. And the work I'm going to talk about is now a couple of years by these two students who spent a semester here and did this work. So the physics of this is rather straightforward at the two limits. Somewhat counterintuitively, at small separation, high density, the system is not strongly correlated, and that's because the kinetic energy, if you imagine every particle is confined in a box or in a circle of RS, then its kinetic energy scales as 1 over RS squared, particle in a box. And the interaction scales as 1 over RS. So if you make RS small, kinetic energy dominates. If you make RS very big, interaction energy dominates. So the two limits are understood. Very small RS, it's a Fermi liquid. Very large RS, it's a classical system that's dominated by Coulomb interaction. So it forms a crystal, Wigner crystal. In between is what's challenging. And the state-of-the-art answer is now from more than a decade ago, but by Drummond and Neitz with quantum Monte Carlo. And it says that there's a Wigner crystal transition at about 30 into a crystal phase. And then the crystal phase magnetic state can change, and that's a very subtle change. This is taken from that paper. How this calculation is done is basically you come up with a variational ansatz that says, I want a liquid. And then you compute the energy. And that's, for example, this, which curve is that? The liquid curve is this red. And then you say, I want a crystal that's anti-ferromagnetic. And then you optimize that ansatz, you get this energy, and then you compare. So for example, here the liquid is lower, so you conclude it's a liquid. Here the crystal becomes lower, so that's the transition. And this is how the calculation is done. And you, as I mentioned, come up with separate ansatz for each phase. I'm going to tell you a little bit about the ansatz. So it's a wave function. P stands for parameters. You're going to make this a variational wave function. So this is a Slater determinant. That's the usual band theory picture of, for example, if you put these as plane waves, then that's the Fermi sea. You put electrons in plane waves and form orbitals. And R1, R2, these little r's denote electron positions. Capital R denotes the collection of all these electrons. So it's a vector, 3 or 2n dimensional vector that gives you a snapshot of where the electrons are, like this picture, where the electrons are. So you can plug in the position into your Slater determinant, you would get a mean field solution. And this ansatz is enhanced a little bit by what's called a Jastrow factor, where it knows about electron correlations. So for example, if you think about this as mimicking the Coulomb interaction, it says if two particles are close, the Coulomb interaction is strong, then the wave function is reduced somewhat. So it's a Jastrow factor. And if you want a Wigner crystal, you put these phi's as Gaussians centered at this crystal states. And of course, in all these phi's and the Jastrow, you could put a lot of parameters and try to optimize them. And you could do better. This is a mean field, and you could add what's called a backflow, which has been pushed by these people in a modern context. But the concept goes back to at least Feynman in the context of understanding helium-3, where these coordinates put in a mean field, but you put in the wave function, not the bare physical coordinates, but rather an x, a backflow coordinate, which is the original physical coordinate of an electron plus a vector, and the vector knows about where the other electrons are. In other words, it's called a backflow. When you put in the orbital, you put in quasi electron coordinate that kind of looks around itself and says, if I have electrons to my right, I'm going to retreat a little bit to the left so that I can know a little bit about correlation. So that's called backflow. And this phase diagram is obtained by Drummond and Needs in this using this sort of method. And then there's an extra kick, which is after you variationally optimize the parameters. Next page, I'm going to tell you a little more about how you do that. You put it into what's known as a diffusion Monte Carlo, where you project the wave function some more. So that's even more accurate than this. And that's the state of the art that gives you this little phase diagram. So here's the kind of the toolkit, the modern, the state-of-the-art method that I was talking about. You do this as a variational ansatz. And the difficulty, just for you to, these are magnified and then magnified some more. If you computed the energy per electron over this range of RS or density where the phase transition is expected to occur, you will see that basically all these phases lie on top of each other. You can't resolve them. They're all the same. So it's a tiny, tiny energy difference that separates these, which this figure blows up. That's why it's an ugly looking figure, but this is really non-trivial work. So variational Monte Carlo, as I mentioned, is simple. It says this: if you come up with an ansatz like psi of r, remember r is the collective coordinates, p denotes all the parameters that you can put in your wave function, then you can evaluate the expectation value of the Hamiltonian. Now, if you notice, this is psi squared. I'm not worrying about the thing being complex. It generalizes easily if the wave function is complex. You cancel one of these, you just get psi h psi, and that's the expectation value at the bottom is psi squared normalization. So variational Monte Carlo at the top level says for each choice of p, a set of parameters, a long vector, you sample, because this is a complicated integral, right? That you don't know this lives in 2n dimensional space. You don't know how to evaluate this. So you sample by, notice that this is a normalization in the bottom, and this is the probability density function. So this whole thing is a normalized probability density, and that's an expectation. So if you can sample, if you could produce Monte Carlo samples of R that are distributed according to psi squared, then you can evaluate the expectation value that would give you the energy. So basically sample the probability density by Monte Carlo, like Markov chain, for example, and then evaluate the energy. And then you could put this in a big loop. You change the parameters again, you evaluate until you hit a minimum, right? So that's variational Monte Carlo. And some of you may have seen this in a machine learning context. as brand new, but this has a long history. Macmillan did it as part of his PhD thesis for liquid helium-4. And I want you to notice this is from 1964. He did 108 atoms, 108 particles. And then for fermions, this is bosons, generalized to fermions. This was non-trivial. It's done by separately Chester and Kalos. This has a Cornell connection. And this was basically the modern incarnation of fermion variational Monte Carlo was invented at Cornell. Now, this was not some hidden pioneer machine learning study. It's a typo simulation of a many fermion study. I think David meant to say many fermion system. And then, almost a decade ago, Kallio and Troyer introduced neural networks into this framework. In their particular case, they looked at mostly spins as in a RBM reduced Boltzmann architecture. So what really does modern machine learning do to this process? It kind of changed the mindset, of course, caused an explosion in this activity. This has been around for a long time. It just hasn't been accurate enough to be systematic in doing a lot of physics. Modern machine learning injected two things. It changed your mindset. It says you could use, it used to be you treasure your parameters, right? Every one is scrutinized. You don't want to introduce more parameters because you can't deal with them. Now, of course, over-parameterizing, right? You throw a lot of parameters at this, and then automatic differentiation allows you to do that process much better with gradient and so on, the technology. Which incidentally, a lot of the modern machine learning technology was invented in this context, right? In physics. And then I had an additional line. I don't remember what it is. I can't see it. Oh, yeah. So I mentioned diffusion Monte Carlo. So diffusion Monte Carlo just takes your optimized final wave function and project it with e to the minus beta h. So basically, it would give you an exact solution, but subject to whatever your fermion wave function defines as the node. In other words, where your wave function changes sign. Diffusion Monte Carlo does not have an ability to change that anymore, but within that boundary condition, it gives you an exact solution. That's why the result that I mentioned is really very sophisticated. So what we're going to do to this problem, which is really what got me sort of convinced to look at this more carefully, is we're going to have a neural quantum state neural network variational wave function that we call MP squared NQS. Neural quantum state and MP squared. I'm going to explain to you now. So this is what we talked about before, this architecture. And what we're going to do is we're going to put in the backflow where the usual backflow, for example, from Feynman just says, if you discover other electrons near you, you push yourself back linearly by some, the distance between you and the next electron times some parameter, so linear function. But we're going to put a message passing, a graph neural network structure in here so that each electron knows about every other electron, but in in a message passing sort of context. And then we're going to put a similar neural network in a JASTRAL so that the usual JASTRAL is written as a cusp condition, like two electrons, basically mimicking the Coulomb interaction, but now it's a full neural network. So that's the first MP is message passing. The next MP is multiple plane waves. In other words, we're going to express all these orbitals in terms of plane waves. Of course, if you just have number of plane waves equal to the number of electrons, that will be the Fermi C. But we give it many more, and we say the coefficients that go into each orbital of the plane waves, you optimize. And this has, you see immediately, you can create orbitals that are Fermi C-like. You can also create orbitals that get localized. So this has a uniform ansatz. We don't tell it anymore whether it should do crystal or do liquid or some other exotic states, hopefully. So again, to remind you, to be truly useful for materials, in other words, to discover new physics and make predictions, it's a very high bar, as I said before. And as of now, it's the development in AI and machine learning has been superbly impressive. In terms of quantum many-body calculations, there's been a lot of activity, but I think actually truly surpassing, most of the activities are in the context of doing a finite system and showing variationally I get very good energy. But to truly surpass state of the art and discover something new has been very, very rare. But it's because it's a very high bar, and we're really still learning how to use this tool. You need to be very high precision, and you need to scale to reasonably large system sizes because a lot of the collective modes need to be accommodated. And you need to be size extensive, and those of you who are chemists know this concept well, meaning that your accuracy, for example, your energy per particle, as you grow in system size, it doesn't decay. Right. So, for example, if you have a lot of parameters, you parameterize a small system, your variational wave function is fantastic. But if your ansatz doesn't scale with system size, with the same number of parameters, its quality might deteriorate. Well, then in that case, you're going to get very good energies here and worse energies here. When you extrapolate, you're much worse off, right, than a less accurate method that's uniform in many cases. So this is difficult to do. So how we did this, the previous slide to set this up, is kind of a targeted use of neural network. Here, the philosophy is a little different, I think, from the majority of the applications in the field, where we don't want to just feed this to a neural network and say, find us an anti-symmetric wave function, because the limit is that typically you see these studies that are at very small system sizes, right? You have a lot of flexibility, but you couldn't scale. And you don't know how the ansatz's accuracy would scale. But this allows us to do like 150 electrons or so. Still, if you think back, very modest after 50 or 40 or 60 years of computer time, the power, how it's increased, we're at this number. But still, this is a important number that allows us to do quite a bit of physics. But at 20, you wouldn't be able to do much, right? And so this difference is what makes that difference. So MP squared NQS, and the kids coded this up, and this is the thing that got my attention, the first piece. So this is the cleaned up version of what I showed you from Drummond and Needs. We reproduced this with state-of-the-art DMC, diffusion Monte Carlo, the Wigner crystal and the liquid. And this is the neural network. It's systematically lower across the board. And that's a very hard bar to meet. And the lowering, if you calculate through this process a structure factor for charge correlation, you discover that it picks up at large RS, signaling a Wigner crystal. In between, depending on how you optimize different initial configuration and stuff, you get scattered answer, and that's this blue region. You get different structure factor. But you can see that a transition has happened without us intervening, but you kind of have this fuzzy signal. So in between, what we did is, in this region, we did transfer learning. We optimize here, and then we do transfer learning. We do that here, and that gives us more accurate crossing. So it detects the Wigner crystal automatically. It revised an RS from 30 to 37. I mean, yeah, we're proud of that, but it's a quantitative thing. What really got our attention was that, so this is the density at RS of 5, and this is 42. You see a density, sort of, that's a sliding crystal, and that's a good thing because it's trying to restore translational symmetry. It didn't quite do that. If it did that perfectly in the crystal, it would be a constant 2. But because we dictate the spins, it couldn't do that because the spins are locked. We don't allow spins to flip. So the usual crystal would be triangular. You would need to have the spins flip. So they form these stripy but sliding crystal in one direction. But the middle is where we looked more carefully in this middle part. Oh, sorry. This is the pair-pair correlation function, and you can see that in the Wigner crystal phase, you have a perfect structure, triangular lattice. And in the middle is what sort of caught our attention. So this is the Fermi liquid. This is the spin-spin correlation function. And in the Fermi liquid, you this is the exchange hole, basically. When you have parallel spins, they repel a little bit. So in the blue is a opposite spin. And this is the Wigner crystal correlation. In the middle, you see this. So the spin spontaneously breaks rotational symmetry, as you see in the Fermi liquid, and it does this nematic correlation. Of course, it's in the correlation. If you look at the density, there's nothing. But in the correlation, depending on your run, this nematic thing would turn in directions. But it's always this, that it's not isotropic. And this is a more careful probe of that, where we take a square lattice system, we come down this way and then go this way. We measure the spin correlation function. So the reference is here. We look at the spin correlation function. And the pink one is reduced by a factor of something like 40, 50, no, 20 something. These are the peaks, and you can see that it's not symmetric, because if you have a triangular lattice coming down, cutting down this line, this is not the same here. You're on the site. But the gray line is the Fermi liquid. It's symmetric because the Fermi liquid is isotropic. But as you go away from the Fermi liquid, the gray, you increase your RS. You can see how this becomes asymmetric about the two sides, and kind of with this peak, the bottom peak position, drifting from here toward the crystal position, this nematic order. So interestingly, so this is a work we did with Parks, Hong Kong Parks group at Harvard. They did these measurements where they saw that there's some coexistence region. So this is inverted. This is density. So a large RS is here. You see the Wigner crystal, and the RS is labeled here. And you can see that there's some transition into Wigner crystal. Here's the Fermi liquid, but in between they saw this large region of couldn't quite tell what this is. And this is very consistent with what we see in this ansatz of this nematic sort of liquid, although this is hand waving this part of the connection, but the size is consistent. We're kind of looking at this more. So this gave us a lot of confidence in this ansatz. And here's a recent thing we did. Connor Smith is the one that did it with Mike Cromie's group at Berkeley, visualizing, and this is really amazing experimental achievement. STM, they visualized this TMD system where they can first identify in these defects. So there are charge defects, these red dots, and then the yellowish ones are isovalent low short range interaction defects, and they can detect that very well. So they can tell us where the defects are. So we put an electron gas in this background that experimentally they determine, and then we try to compare. So this is at low densities. These are STM images, and the little red dots are the defects. And the bright dots are electron density, high density region. And you can see at these densities, so these are RS, you see quite big, 39, 41. You see a solid, right, that has disorder because the charge defects control them. And this is our simulation with the same experimental disorder. And you can see that, it's quite remarkable given that it's a patch and the simulation is done in a periodic system. When you increase the electron density, fixing the defects, and this is what STM sees, and you can see that these local rivers start to get connected and it gets liquidish because the density is increasing as you go to the right. And this is the simulation. And this stuff in the past, we could not, with what I call the state of the art, we could not do this because we would have to solve, to come up with a determinant, we would have to solve some sort of a mean field. When you put in a mean field with this disorder, it doesn't know about the interaction well enough so that this sort of thing would completely get missed. So in other words, balancing the two correctly, we would never be able to find the orbitals. And here, the neural network finds it, right? Finds it through optimization. So, and now this is imaging now in the presence. So before it was predominantly just charge defects. Now there are in this blob, there's a few charge defects, but they start to investigate the short range defects, the isovalent defects. So we know there are a lot of them. They can give us the density, so we put that in as well. So as a function of electron density, you can see that it becomes a liquid. And we're going to focus on this particular density. We know from experiment, we're going to study the effect of the short-range interaction. So we still put in the long-range interaction, but we don't have the short-range defects. And you can see that it's a liquid, right? The electrons are, it can't, Anderson localization in the system, though, the density is quite spread out. So it's this same system, but without the short-range defect. We see this picture. And then we add 25%. So the defect positions are random. We sample their random positions. We take 1/4 of them. We put it in. We see this pattern. We put 50%. We see this pattern. We see 100% put their defects in. And this is the simulation. And you can see the two are, you'd be hard pressed to tell which one is which. So we think we have a wonderful tool now to study, the interplay between Anderson localization and Wigner crystal strong correlation. I'm running way behind, so I'm going to zip through this. So this is now adding a Moiré potential. So we have this, the Moiré potential looks like this, and this corresponds to, 26 degrees. You form a triangular lattice, for example. And you just have this Hamiltonian, that's the Jellium Hamiltonian, but now with a interaction. So now there are two parameters, the Jellium RS, or three parameters, and the depth of the Moiré potential, and then, of course, how many electrons you put in, and whether that's commensurate with the Moiré periodicity or not. So before we had studied triangular lattice, I think this Una's group had looked at this same system as well. There's what I mentioned before, you would have a Néel order 120 and then paramagnetic metal. And then we studied this 60 at a fitting where we have one electron per two local minima in a honeycomb, and it has this interesting feature of a spontaneous ferromagnetism, ferromagnetic metal forming, and then a charge density wave. So Connor was playing with this, and he was looking at 1/4 now with the neural network. And we were really surprised by what he found. So this is depicting the situation. So I think this plots 8 minima in a honeycomb structure. There are 2 electrons. So 1/4 by this particular definition, 1/4 fitting. So basically 1 electron per 4 local minima, and spin up and spin down is depicted this way. And this is just a potential well. If you do state-of-the-art, the usual toolkit I told you about, you will see this state. You will see a valence bond anti-ferromagnetic solid, which is interesting, very interesting. So each electron would kind of spontaneously hop along 2 minima, and this is different spins, right? So anti-ferromagnetic, and they form this valence bond. Of course, it's a symmetry breaking state, right? But it's a solid. And that's what you would find. So this one spin is spread over 2. What Connor found with the NQS is instead this structure, where a pair of electrons, so 2 electrons, one up, one down, would form a pair on this hexagon. And the pair is mobile. So when you measure them, I'll show you how we know that it's mobile. Okay, next page maybe. So a pair on every 6, and then it's a sublattice. It forms a triangular lattice of crystal. So paired Wigner crystal. And this is weird because there's no attraction to form a molecule, and this has a molecule. It's a pair. The whole thing is repulsive, assisted by these periodicity, the Moiré pattern. How do we know it's not hallucinating? Well, we can take this orbital. So if we do just our best with diffusion Monte Carlo projection, this state is stable. But now that the NQS told us about this, we could cheat. We can construct the orbitals here, feed it into DMC, it stays there, it leads you to a lower energy than the left. So this is telling you about properties. I think I'm gonna just basically skip this. So there's a crystal phase, paired Wigner crystal phase, where spontaneously it breaks the two sublattice symmetry and forms this crystal that consists of pairs. And at lower potential well depth, it's a metal with constant density. But as you increase the depth, it locks into one of these states. And the reason we know that this pair is mobile is within each pair, if you calculate the angle, relative angle between them, the distribution looks like this, right? So maximum probability, they're 180 apart, but there's a finite probability everywhere, and they're circling. If you look at the density, it's a constant on the ring. This state, interestingly, was predicted by Ashcroft, I think around the time I was a graduate student there. But it did not register. It's so interesting, and he predicted for the electron gas, which turns out to be incorrect. The electron gas, no matter how hard people try, those states are just not, they're way higher. But it's interesting with Moray potential, this happened. So, and there's a chance now experimentally, because the setup is already, this is easy to engineer, to see this and validate this. And in between, I didn't mention when it goes into this molecular solid phase from a liquid, whether there's the possibility of a superfluid or a supersolid. I think the system size is still too small to do that, but tantalizing possibility. So this last bit, I'm going to zip through, is an anonymous Wigner Hall crystal. So it's a topological Wigner crystal. It has triggered a lot of interest, spurred by the pentalayer graphene experiments. Though it looks like that's not the state in that system. But the predictions are many here, mostly based on Hartree-Fock. So then does this phase, which is a topological Wigner crystal, does it survive with correlation? I want to remind you that with Hartree-Fock in the electron gas, the first one we talked about, if you did Hartree-Fock, it would tell you the Wigner crystal transition happens at 2, RS of 2. In reality, it happens at 40. So it's a factor of 20 difference in linear dimension, a factor of 400 error in the density, critical density. And so you certainly want to ask, is Hartree-Fock just telling you something crazy? So this is work done by Agnes Balante, who's a postdoc here. And we look at this lambda jellium Hamiltonian, where this is the 2-deg that I've been talking about, and we add this spinor term for topology, and then we project. And oh yeah, this is the Hartree-Fock phase diagram. It tells you that there's large patches, these reddish things, that are HC states, Hall crystal, anomalous Hall crystal states, that basically is a Wigner crystal, but has a Chern number. But the transition at the bottom is at RS of 2, as I mentioned to you before. So, and I don't see what I put at the bottom, but here's our result for this lambda jellium model described in that paper at the bottom. It turns out it does survive. It's a very small patch. It does survive. Just to compare with the Hartree-Fock phase diagram, if you squish this and put it on the same scale, this is the many-body, this is the neural network phase diagram, and that's the Hartree-Fock phase diagram, okay? So the topology is still here, this red thing, but it's a very different set of parameters. And there's an interesting, so this is at 37, but it's interesting how when you turn on topology, and that's the topology, kind of think about it as controlling how strong Berry curvature is. There's a rapid, it caves in dramatically, the crystal kind of takes over a lot earlier. And these are characterizing, so this is the HC phase, the crystal, the correlation, and the momentum distribution. and churn number is labeled in the next slide. But there's also a halo Wigner crystal, which is interesting that it has a momentum distribution 0 here, and so kind of a center. So I mentioned to you Connor and Agnes. These are the main people, two really spectacular postdocs who did a lot of work, and we benefited. These are young people who contributed to the different projects. Miguel Morales is a colleague of mine at CCQ, and we benefited from the collaboration with experimental groups, Feng Wang's group and Cromie's group and Park's group. So yeah, so I told you about these sort of 4 different stories related to different 2-dimensional models. Again, I hope I convince you that with machine learning and neural quantum state, if you use it properly, I don't know how proper we are, but certainly not blindly, then it really does. It's exciting and shows a lot of potential. Thank you very much.
Thank you.
Thank you,
I think
Shiwei.